This presentation for the Vital Syllabus looks in some detail at what are called the Singularity Principles, namely a set of recommendations that are intended to increase the likelihood that oncoming disruptive technological changes will have outcomes that are profoundly positive for humanity rather than deeply detrimental. The principles are split into 4 sections. Analysis of the goals and outcomes that may arise from particular technologies. Analysis of the characteristics that are desirable in technological solutions. Analysis of methods to ensure that development takes place responsibly. And a meta-analysis. Principles about how this overall set of recommendations might itself evolve further over time, and principles for how to increase the likelihood that these recommendations are applied in practice rather than simply being some kind of wishful thinking. The principle of question desirability starts with the recognition that just because we believe we could develop some technology, and even if we have some desires to develop that technology, that's not a sufficient reason for us to actually go ahead and develop it and deploy it. After all, once a project starts with the goal of developing some technology, the project sometimes develops momentum that can carry it forward almost of its own accord. People involved tell themselves and each other that there's already a commitment to continue the project. They may feel they're in a race with competitors. They may feel a sense of loyalty to the project. They may feel an obligation to fellow team members, or to bosses, or to others who are assumed to be waiting for the technology. They may desire to ship their product to the world to show their capabilities. But the result of this inertia could be outcomes that we later bitterly regret. Therefore, the principle of question desirability urges that we take the time to write down what we assume are the good outcomes we will obtain from the technology to be developed. Once these assumptions have been written down, it allows for a more thoughtful and considered review. The principle also urges that we consider other methods for achieving these intended outcomes, other methods apart from the particular technology that has somehow caught our fancy. This separation in analysis of desired outcomes, also known as requirements, from possible solutions, is a vital step to avoiding unintended consequences of technologies. We may find better, safer, more reliable ways of achieving the outcomes that we have in mind. The principle of question desirability also recommends that we should, in any case, challenge assumptions about which outcomes are desirable, and we should be ready to update these assumptions in light of improved understanding. Finally, we should also avoid taking for granted that agreement exists on what will count as a good outcome. That takes us to the next principle: clarify externalities. Recall that an externality is an effect of a project or the effect of an economic transaction that is wider than the people directly involved. Examples of externalities include noises that can be heard by more people, smells that can distract more people, pollution that can impact people's livelihoods, resource depletion, cultural chaos, and a general loss of resilience. The principle of clarify externalities draws attention to the possible wider impacts, both positive and negative, from the use of products and methods beyond those initially deemed central to their operation. The principle seeks to ensure that these externalities are included in cost-benefit calculations. Therefore, we should not just consider metrics such as profit margin, efficiency, time to market, and crushing competitors. We need to consider broader measures of human flourishing, such as those reviewed in the philosophy and transhumanism areas of the Vital Syllabus. What makes this analysis possible is the effort taken, in line with the question desirability principle, to write down the intended outcomes of the technology to be developed. What makes this analysis more valuable are the principles of require peer reviews and involve multiple perspectives, to which we now turn. The alternative to requiring peer reviews is that we trust the people who are behind a particular project. We may feel that they have a good track record in creating technologies and products. We may feel that they have outstanding talent. Therefore, we might think no peer review would be required. Now, that might be acceptable for projects that are sufficiently similar to those undertaken in the past. However, new technologies have a habit of bringing surprises, especially when used in novel combinations. That's why independent peer reviews are required, involving external analysts who are not involved with the initial project team. These analysts should ask hard questions about the assumptions made by that team. What's more, this analysis phase into the desirability of products and methods in pursuit of goals that have already been stated should involve people with multiple different skill sets and backgrounds. This should include expertise in law, economics, and human factors, as well as designers, scientists, and engineers. To be clear, these independent analysts won't necessarily have a veto over decisions taken by the project team. However, what is required is that the project team, along with their sponsors, take proper account of questions and concerns raised by independent analysts. That proper account needs to observe two further principles: analyze the whole system and anticipate fat tails. What's meant by the whole system is the full set of things that are connected to the technology that could be developed and deployed. Upstream influences, downstream magnifiers, and processes that run in parallel. It also includes human expectations, human beliefs, and human institutions. It includes aspects of the natural environment that might interact with the technology. And critically, it includes other technological innovations. When analyzing the potential upsides and downsides of using the new technology that we have in mind, we need to consider possible parallel changes in that wider whole system. For example, rather than simply analyzing how a new piece of artificial intelligence might behave in the environment as it exists today, we should consider possible complications if other pieces of new artificial intelligence, including adversarial technology or new forms of hacking, are introduced into the environment as well. This analysis might lead to the conclusion that the new technology would, after all, be more dangerous to deploy than was first imagined. Or it could lead to design changes in the new technology so that it would remain beneficial even if these other alterations in the environment took place. The principle of anticipate fat tails urges us to remember that not every statistical distribution follows that of the well-known normal curve, also known as the Gaussian bell curve. In many circumstances, it's true that once we observe the mean of a set of observations, often denoted by the Greek letter mu, and also the standard deviation of these observations, known as sigma, we can be confident that new measurements more than 3 standard deviations away from the mean will be unlikely. They'll be seen only around 3 times in 1,000. And for a new measurement that is more than 6 standard deviations away from the mean, you would have to wait on average more than 1 million years if a new measurement was made every single day. However, our initial observations of some data might lead us astray. The conditions for the distribution of results being normal might not apply. These conditions require that the outcomes are formed from a large number of relatively small individual influences which are independent of each other. When instead there are connections between these individual influences, the distribution can change to have what are known as fat tails. Outcomes that are more than 6 sigma away from the previously observed mean, or even more than 20 sigma away from it, can arise, giving everyone a horrible surprise. That possibility would change the analysis from how might we cope with significant harm, such as a result 3 sigma away from the observed mean, to could we cope with total ruin, such as a result that is, say, 20 sigma distant. In practical terms, this means our plans for the future should beware the creation of monocultures that lack independence and diversity. Cultures in which all the variations can line up and move in the same direction at once. We should also beware the connection of hidden interactions, such as the shadow links between multiple different financial institutions that precipitated the shock financial collapse in 2008. If there are reasons to foresee such outcomes, it means we need to rethink our plans for the new technology. Otherwise, the world might experience a shock outcome from which there is no prospect of any recovery, perhaps for generations, perhaps indefinitely. That takes us from the Singularity Principles for the analysis of the goals and outcomes that may arise from particular new technologies to the Singularity Principles for the analysis of the characteristics that are desirable in technological solutions. The first principle in this second set is the principle of reject opacity. The principle of reject opacity means to be wary of technological solutions where we don't understand how they work. These solutions are sometimes called opaque or black box because we cannot see into their inner workings in a way that makes it clear how they are able to produce the results that they do. This is in contrast to solutions that can be called transparent, where the inner workings can be inspected to a sufficient degree that we do understand why they work. The principle also means that we should resist scaling up such a solution from an existing system where any failures could be managed into a new, larger system where any such failures could be ruinous. As it happens, many useful medicinal compounds have mechanisms that are, or were, poorly understood. One example is the drug aspirin, probably the most widely used medicine in the world after its introduction by the Bayer Corporation in 1897, whose mechanism of action was not understood until 1971. Wikipedia has a category called Drugs with Unknown Mechanisms of Action that, at the present moment, has 68 pages. This includes the page on general anesthetics. Many artificial intelligence systems trained by deep neural networks have a similar status. It is evident that such an AI often produces good results in environments that are well defined. But it's not clear why the system can produce these results. It's also unclear when such an AI system can be misled by so-called adversarial input, or what are the limits of the environments in which that AI will continue to function well. So long as the overall process is being monitored and actions can be taken to address failures before these failures become ruinous or catastrophic, opaque systems can have a useful positive role in increasing human well-being. But where there are risks of failures escalating beyond the ability of any intervention to fix in a timely manner, these opaque systems need to be rejected. Instead, more work is needed to make these systems explainable and to increase our certainty that the explanations provided by this understanding accurately reflect what is actually happening inside the technology rather than being a mere fabrication that is unreliable. The principle of promote resilience means we should prioritize products and methods that make systems more robust against shocks and surprises. If an error condition arises or an extreme situation, a resilient system is one that will take actions to reverse, neutralize, or otherwise handle the error rather than such an error tipping the system into an unstable or destructive state. An early example of a resilient design was the so-called centrifugal governor or flyball governor, which James Watt added to the steam engine. When they rotated too quickly, the flyballs acted to open a valve to reduce the pressure. Another example is the fail-safe mechanisms in modern nuclear power generators, which force a separation of nuclear material in any case of excess temperature, preventing the kind of meltdown which occasionally happened in nuclear power generation with earlier designs. Following the COVID pandemic and the consequent challenges to supply lines that had been over-optimized for just-in-time delivery, there has been a welcome rediscovery of the importance of designing for resilience rather than simply for efficiency. These design principles need to be further elevated. Any plans for new technology should be suspended until a review from a resilience point of view has taken place. The principle of promote verifiability states that we should prioritize products and methods where it is possible to ascertain in advance that the system will behave as specified without having bugs or defects in it. We should also prioritize products and methods where it is possible to ascertain in advance that there are no significant holes in the specification, such as a failure to consider interactions with elements of the environment or combination interactions. In other words, the product is specified to behave in various ways in a variety of different circumstances in order that particular goals or requirements are met, as previously discussed in the section on question desirability. In turn, the product is designed and implemented using various techniques and technological components in order that it behaves in line with the specification. The principle of promote verifiability urges attention on ways to demonstrate the validity of both of these steps, that the specification meets the requirements without having dangerous emissions or holes, and that the implementation meets the specification without having dangerous defects or bugs. These demonstrations must be more rigorous than someone saying, Well, it seems to work. Different branches of engineering have their own subdisciplines of verification. The associated methods deserve attention and improvement. The principle of promote auditability has a similar goal to promote verifiability. Whereas promote verifiability operates at a theoretical level before the product is introduced, promote auditability operates at a continuous and practical level once the product has been deployed. The principle urges that it must be possible to monitor the performance of the product in real time in such a way that alarms are raised promptly in case of any deviation from expected behavior. Systems that cannot be monitored should be rejected. Systems that can be monitored, but where the organization that owns or deploys the system fails to carry out audits or fails to investigate alarms promptly and objectively, should be subject to legal sanction in line with the principle insist on accountability that will be reviewed later in this presentation. Systems that cannot be audited or where auditing is substandard inevitably raise concerns. However, if auditability features are designed into the system in advance, at both the technical level and the social levels, this will help ensure that technology boosts human flourishing rather than behaving in deeply regrettable ways. It's the same with verifiability. Systems that have been designed to support verifiability are, other things being equal, more likely to produce technology that is truly beneficial. The principles that have been covered so far are, to be frank, challenging and difficult. Compared to these ideals, any given real-world system is likely to fall short in a number of ways. That's unfortunate, and steps should be taken as soon as possible to systematically reduce the shortfall. In the meantime, another principle comes into play. It's the principle of being open to users and potential users of a piece of technology about any known risks or issues with that technology. It's the principle of clarify risks to users. Here, the phrase user includes developers of larger systems that might include the original piece of technology in their own constructions. The kinds of risks that should be clarified before a user starts to operate with a piece of technology include any potential biases or other limitations in the sets of data used to train these systems, any latent weaknesses in the algorithms used, including any known potential for the system to reach unsound conclusions in particular circumstances, and any potential security vulnerabilities, such as risks of the system being misled by adversarial data or having its safety measures being edited out or otherwise circumvented. When this kind of information is shared, it lessens the chances of users of the technology being taken by surprise when it goes wrong in specific circumstances. This information will also allow these users to provide necessary safeguards or to consider alternative solutions instead. Cases where suppliers of technology fail to clarify known risks are a serious matter, which we'll reach in a moment. But first, there's one other type of clarification that needs to be made. The principle of clarify trade-offs recognizes that designs typically involve compromises between different possible ideals. These ideals sometimes cannot all be achieved in a single piece of technology. For example, different notions of fairness or different notions of equality of opportunity often pose contradictory requirements on an algorithm. Rather than hiding the design choice, it should be drawn to the attention of users of the technology. These users will, in that case, be better able to make good decisions about how to configure or adapt that technology into their own systems. Another way to say this is that technology should, where appropriate, provide mechanisms rather than policies. The choice of policy can, in that case, be taken at a higher level. That takes us from the Singularity Principles for the analysis of the characteristics that are desirable in technological solutions to Singularity Principles for the analysis of methods to ensure that development takes place responsibly. The first principle in this third set is the principle of insist on accountability. The principle of insist on accountability aims to prevent developers from knowingly or recklessly cutting key corners in the way they construct technology solutions. A lack of accountability often shows up in one-sided license terms that accompany software or other technology. These license terms avoid any acceptance of responsibility when errors occur and damage arises. If something goes wrong with the technology, these developers effectively shrug their shoulders regarding the mishap. That kind of avoidance needs to stop. Instead, legal measures should be put in place that incentivize paying attention to and adopting methods that are most likely to result in safe, reliable, effective technological solutions. As always with legal incentives, this will require high caliber people who are well informed and up to date, working on the definition and monitoring of these incentives. As a special case of insisting on accountability, the principle of penalize disinformation insists that penalties should be applied when people knowingly or recklessly spread wrong information about technological solutions. Communications that distort or misrepresent features of a product or method should result in sanctions proportionate to the degree of damage that could ensue. An example would be if a company notices problems with its products as a result of an audit, but then fails to disclose this information and instead implies that there is no issue that needs further investigation. Again, this principle will require high caliber people who are well informed and up to date, working on the definition and monitoring of what counts as disinformation. The payment and training of such people is likely to need to be covered from public funds. Another initiative that is likely to need public coordination rather than arising spontaneously from marketplace interaction is a strong preference for collaboration on matters of safety rather than a headlong competitive rush to release products as quickly as possible in which shortcuts are taken on quality. Hence the principle of design for cooperation. One example of this is that public policy could give preferential terms to solutions that share algorithms as open source without any restriction on other companies using the same algorithms. That's design for cooperation. Public funding and resources should also be provided to support the definition and evolution of open standards, enabling the spirit of collaborate before competing. Frankly, the definition and timely evolution of open standards is a hard task. It will require high caliber people who are well informed and up to date, working on the definition and evolution of these standards. In turn, this is likely to require public subsidy to ensure that this happens in an effective manner that can win the respect and trust of the companies whose solutions will be impacted. One factor that has always helped to design and produce new technology is previous technology, including tools and components. One use of existing technology is the construction and operation of test environments in which new technology can be put under stress in a variety of circumstances before being released for wider deployment. Designing and using test environments in an efficient, effective way is a major engineering discipline in its own right. There's little point in repeating the same test again and again with minimal variation. That would consume resources and delay product releases with little additional benefit. Testing is, therefore, a creative activity. On the other hand, the more that test processes can be automated, the easier it can be to ensure that they are completed in a comprehensive manner. One new factor in recent times is the ability for new technology to be tested in virtual environments, that is, in simulations. The principle of analyze via simulations urges that attention be given to virtual reality simulations in which new products and methods can be analyzed in advance of real-world deployment with a view to uncovering potential surprise developments that might arise in stress conditions. To be clear, each virtual reality simulation is likely to have its own limitation and drawbacks. They won't fully anticipate all the eventualities that may occur in real-world situations. However, over time, these simulations can improve, becoming more and more useful and more reliable. Creating and maintaining best-in-class virtual reality simulations is likely to require the support of public funding and resources. Discussion of the role of simulated virtual environments brings us to the last principle in this section, the principle of maintain human oversight. An increasing role in the development of new technology is being played by automated systems operated via artificial intelligence. These systems assist with the specification, design, implementation, verification, testing, monitoring, and analysis of new technology. These systems can make the overall process of development faster and more reliable. However, although recommendations for next steps in developing new products and methods will increasingly originate from software or AI, control needs to remain in human hands. We must ensure that such proposals arising from automated systems are reviewed and approved by an appropriate team of human overseers. That's because our AI systems are, for the time being, inevitably limited in their general understanding. It's also the case, of course, that any one human is likewise limited in their general understanding. That's why the principles of require peer reviews and involve multiple perspectives covered earlier come into play. And it's the same with AI. We should look for ways to have multiple different independent AIs review the recommendations for new product development. And in all cases, the final decisions in any contentious or serious matter should pass through human oversight. This also means that we humans need to regularly practice making independent decisions without becoming overly dependent on AI tools that might, in unexpected circumstances, mislead us or let us down. That takes us from the Singularity Principles for the analysis of methods to ensure that development takes place responsibly to the Singularity Principles about how these recommendations might themselves evolve further over time, and the principles for how to increase the likelihood that this set of recommendations are applied in practice rather than being simply some kind of wishful thinking. The first principle in this final set is the principle of build consensus regarding principles. The principle of build consensus regarding principles urges that this set of principles be discussed widely to ensure broad public understanding and buy-in, with conformance in spirit as well as in letter. We should also be ready to update these principles if discussion makes such a need clear, provided the potential change has been widely reviewed beforehand. We can be guided in these discussions by applying many of the same singularity principles, which were initially about the development of technology, to the development of the principles themselves. This includes the singularity principles about goals and outcomes, question desirability, clarify externalities, require peer reviews, involve multiple perspectives, analyze the whole system, and anticipate fat tails. It also includes the singularity principles about the characteristics that are desirable in solutions and methods. Reject opacity, promote resilience, promote verifiability, promote auditability, clarify risks to users, and clarify trade-offs. It's still comparatively early days in this discussion to build consensus, but the principles presented here are a good starting point. The principle provide incentives to address emissions states that where any of this set of principles cannot be carried out adequately, measures should be prioritized to make available the additional resources or suitably trained personnel that can fill these gaps. This may involve extra training, provision of extra equipment, transfer of personnel between different tasks, altering financial incentive structures, updating legal rules, and so on. However, if the gap grows too large between the recommendations of the principles and prevailing industry practices, something more drastic is needed. That brings us to the principle of halt development if principles are not upheld. In case any of these singularity principles cannot be carried out adequately and measures to make amends are blocked, any further development of the technology in question should be halted until such time as the principles can once again be observed. This may be viewed as a shocking principle, but it was applied very successfully as part of the revolutionary lean manufacturing culture developed in Toyota in Japan from the 1930s onward. Toyota executives realized it was actually to the competitive advantage of their company if each and every employee on their production line was able to pull a cord on noticing a significant problem with the production to temporarily halt production of that product. This break meant that wide attention was quickly brought to bear on whatever quality issue had been noticed. production throughput slowed down in the short term, but quality throughput and reliability increased in the medium and longer term. But as just noted, adopting this principle means a slowdown in production in the short term, which some companies may consider to put them at a fundamental disadvantage against faster-moving competitors. Moreover, some companies, out of their own bias towards thinking their solutions have very special qualities, may not agree with the appropriateness of some of the principles given earlier. They may wish to rush on regardless. As in the famous phrase that was Facebook's motto for many years, they are prepared to move fast and break things, thinking that if things do get broken, they will be easy enough to fix afterwards. That thought, move fast and break things, is opposed by an idea expressed at a lecture in 1923 at Cambridge University by biologist J.B.S. Haldane, entitled Daedalus, or Science and the Future. Haldane reflected on the growing power of science. Haldane noted the progressive increase in these powers, which he expected to continue. He suggested that these powers are only fit to be placed in the hands of a being who has learned to control himself. He went on to say, in a phrase that others have subsequently often repeated, that man armed with science is like a baby armed with a box of matches. No one likes to be told that they are like a baby, especially if they have a past history of developing remarkable technology. However, from a certain point of view, we all lack sufficient forethought and control to simply move fast and break things, when what we might break has such explosive potential. So how do we ensure that production is halted, if necessary, before it reaches an explosive failure? The final principle in the set is consolidate progress via legal frameworks. The principle states that we should embed aspects of these principles in legal frameworks to increase the chance that they will be followed. There should be appropriate penalties for violating these frameworks, just as there are penalties, for example, in place when companies violate any of a range of existing regulations on health and safety, or on truthfulness in advertising, or on the presentation of financial information. We should also be ready to update these legal statutes promptly if it becomes clear that they need amending following appropriate review. This is no easy task. It will require high caliber politics to ensure it works well, and it will also require high caliber geopolitics to ensure a suitable level playing field on the international stage. See other videos from the Vital Syllabus about ways to improve our political and geopolitical processes. That concludes a look at the long form of the Singularity Principles. As a reminder, they can also be expressed in a shorter form. Namely, we should be sure that we know what we are hoping to accomplish, rather than us merely drifting in some direction because it sounds nice, or has some alluring features, or it seemed like a good idea the last time that strategy was reviewed. We should also be sure we know the products and methods that are the most likely to serve these goals well, rather than us persisting with products or methods that happen to make us feel comfortable and which have given us some good results in the past. And we should be sure we know how we will manage any surprises arising en route to our goals, rather than us being caught flat-footed as the victim of inertia or denial when unexpected signals start showing on our radars. Many questions can still be asked about turning these singularity principles into practical reality. There's further discussion of related examples in a number of other videos in the singularity portion of the Vital Syllabus. For example, take a look at the discussion AGI or not AGI, fundamental choices, which is about how to decide whether and in what circumstances we should accelerate research toward artificial general intelligence, or whether instead we should put a global brake on all such work. Thank you for your interest in the Vital Syllabus.